Hi everyone, today we will take up some important questions from the atomic structure for NEET and UG exam. Okay, so these are the question number 1, 2, 3, 4, 5 and 6. Okay, so let's take up this 6 question for today. So first you take a screenshot and you can solve it by yourself. Just try it. Okay students, let's start from question number 1. When electrons are de-exciting to the ground state from nth orbit of hydrogen atom, 15 spectral lines are formed. So the shortest wavelength among these will be, okay. So we have to find the spectral lines which have the shortest wavelength, okay, and we have to also find the shortest wavelength, okay. So the electron jumps from n orbit to ground state, okay, and there are 15 spectral lines. So for this, we have to find the value of n. So it is given by n minus 1 by 2. This is the formula, okay, which gives the number of spectral lines. From here, let's find out the value of n. N square minus n is equal to 30. N square minus n minus 30 is equal to 0. So we get a quadratic equation. So let's find the value of n square. So products 30 and difference 1, so 6 and 5. 6n plus 5n minus 30 is equal to 0. n minus 6 plus 5 n minus 6 is equal to 0. So n minus 6 n plus 5 is equal to 0. N equal to 6 or n equal to minus 5. Sorry, n equal to minus 5. Okay, so since the n cannot be negative, so we have to neglect this value. So we'll take n equal to 6. Okay, so the electron jump from n equal to 6 orbit to ground state n equal to 1. Okay. So here 6 to 5, 6 to 4, 6 to 3, 6 to 2 and 6 to 1. Okay, so he asks the shortest wavelength. Okay, so here we have already learned that longest wavelength will be the 6 to 5 transition and shortest wavelength is equal to 6 to 1 transition. Clear? So let's find out the wavelength using the Rydberg formula. 1 by lambda is equal to RH 1 by 1 square minus 1 by 6 square. 1 by lambda is equal to RH 1 minus 1 by 36 RH 35 by 36. So here lambda is equal to 36 by 35 r. Okay, 36 by 35 r. So this is the shortest wavelength transition. So the correct answer is 4. Okay. Then this is how we solve the problem. Let's move on to the next question. Okay, question number 2. In which of the following transition the wavelength will be minimum? Okay. So for this we have to find out the wavelength, and let's compare. So here let me write the Rydberg formula. 1 by lambda is equal to r 1 by, for this one, 1 square by 1 by 3 square. Okay, so similarly 1 by r lambda is equal to r 1 by 4 square minus 1 by 6 square. 1 by lambda is equal to r 1 by 2 square minus 1 by 4 square. 1 by lambda is equal to r 1 by 1 square minus 1 by 2 square. So let's compare the value. 1 minus 1 by 9, 1 by 16 minus 1 by 36, 1 by 4 minus 1 by 16, then 1 minus 1 by 4 is equal to 8r by 9. Okay, 16 144, so 5r by 144, then 16, so 3r by 16, 4 minus 1, okay, then 3r by 4, 3r by 4, okay. This is 1 by lambda, which is wave number, so let's convert into lambda. Lambda is equal to 9 by 8r, lambda is equal to 144 by 5r, lambda is equal to 16 by 3r, lambda is equal to 4 by 3r, okay. So here he asks the minimum wavelength, okay. We have to select the one having the smallest value, I think. So with this 145 by r, this will not be the value. This 16 by r, 3, 4, 3, 5, 15. This cannot be the smallest value. So let's 9 by 8 and a 4 by 3. Okay, we can compare this one. 8 by 9, we get something around 1.12. Okay, around. Then 4 by 3, we get around 1.33 something. Okay, so here the smallest value will be 1.12. okay, this has the smallest value, so the correct answer will be n equal to 3 to n equal to 1 transition. Okay, this transition will have the minimum wavelength. Okay, so this is the second one. Let's move on to the third question. If the potential energy of hydrogen electron is minus 3.02 electron volt, then which of the following excited level is electron present? Okay. For hydrogen electron. Okay, students, so let's try this. So for this we have to apply the postulates of Bohr, okay, about the energy. So we've learned that it is given that potential energy is equal to minus 3.02 electron volt. Okay. So we have to find out in which energy level this electron is present. Okay. So we've already learned that potential energy is equal to 2 times the total energy. Potential energy is minus 3.02 electron volt is equal to 2 into total energy is given by minus 13.6 z square by n square. So here minus 3.02 is equal to 2 into minus 13.6, z is 1 for hydrogen, atomic number is equal to 1, so n square, minus cancel, so n square is equal to, let's multiply this 2, so 27.2 divided by 3.02. Then n square is equal to, I think when you divide this, you get 9, okay, 9.00 something, so you get 9, so n is equal to 3. N equal to 3. So here, students, n equal to 1, n equal to 2, n equal to 3, n equal to 4, okay. N equal to 4 is the ground, n equal to 1 is the ground state, n equal to 2 is the first excited state, okay. N equal to 3 is the second excited state, okay. Don't get confused in the exam, okay. So he asks in which of the following excited level this is the electron present, okay. Since I get n equal to 3, my answer will be the second, okay, second. n equal to 3 means second. So here the correct answer is B, okay, not C, okay. This is question number 3. Then let's move on to question number 4. What is the potential energy of an electron present in the N cell of Be3 plus ion? Okay, Be3 plus is a hydrogen-like ion, hydrogen-like system having only one electron. Okay, so we have to find out the potential energy. Okay, potential energy we have already done in the previous question, 2 times total energy. Total energy, so 2 into total energy is minus 13.6 Z square by N square for hydrogen-like system. Okay, 2 into minus 13.6 into Z. For beryllium, atomic number Z is equal to hydrogen, helium, lithium, beryllium 4. Then it belongs to N cell, KLMN. Okay, so N equal to 1, 2, 3, 4. Okay, so 4 square by 4 square. So it will 4 cancel. So 6 or 12, 27.2 electron volt. 13.6. Okay, this is the answer. So the correct answer is option number D. Okay. So let's move on to the fifth one. The energy required to ionize a helium atom is equal to 24.6 electron volt. Then the energy required to remove both electrons from the helium atom would be, okay. Okay, so students, the energy required to remove an electron from an atom is we call as ionization energy. Okay, ionization energy is the energy required. So the sign of ionization enthalpy is positive. Okay, so let's take helium atom. Then I remove one electron. Then this is first ionization energy, and the amount of energy required is 24.6 electron volt. Then suppose I have to remove the second electron again. So this will be the second ionization energy, which we don't know. Okay, we don't have the value here. Okay, so he asks the energy required to remove both the electron. Okay, means we have to find the sum of first ionization energy and the sum of second ionization energy. Okay, we have to find the sum. Okay, so first let's find this. So IE2 is given by 13.6 Z square by N square electron volt is equal to 13.6 into Z square atomic number helium 2 square by since the electron belongs to first cell 13.6 into 4, that is 6 for 4 4 12 1 54.4 electron volt. Okay, here we use positive sign. Okay, since it is we express energy in terms of ionization energy. Okay, so the first ionization enthalpy is 24.6 electron volt, and the second ionization enthalpy is 54.4 electron volt. Okay, let's find the sum. 24.6 54.4 0197, so 79 electron volt. So the correct answer is C. Okay, so then let's move on to the last one. The orbital angular momentum of an electron in a single electron system, okay, is √3 h by pi. Okay, so this is the orbital angular momentum is given by √3 h by pi. which of the following angular momentums values are not possible? Okay, he asks which are not possible for this electron in the Bohr orbit. Okay, so orbital angular momentum is given by, we have already learned, root over L plus 1 h upon 2 pi h by into h by 2 pi, and the angular momentum on the Bohr orbit is given by this L equal to mvr is equal to integral multiple of h by 2 pi. Okay, so we have to apply these two formulas here. So first let's find the value of L. Okay, so this is orbital angular momentum, so this value will be equal to this relationship. So h cancel, pi cancel, then square root of L plus 1 is equal to 2 root 3. Okay. Squaring both sides, we have L plus 1, 2 root 3 into 2 root 3 means 12, 4 into 3, okay, 12, okay. L plus 1 is equal to 12. That is, I think, L equal to 3. 3 plus 1, 4, 4 into 3, 12, okay. So, L equal to 3. So first, we find the value of L. Then let's find out in which orbital does it belongs. L equal to 0, 1, 2, 3. 0 S, P, D, F. Okay, here the electrons belong to F. Okay, F. Okay, which of the following angular momentums are not possible for this electron? Okay. So students, so angular momentum in the Bohr orbit is given by nh by 2 pi. Okay, so when n equal to 7, when n equal to 7 means it has f orbital, so this is possible. When n equal to 5, it has f orbital, so this is possible. Okay, so C, for option number C, it is given by 2h by pi. Okay, so let's express in this form. 2 pi by 4h by 2 pi. Okay, so it can be given as 4h by 2 pi. So for n equal to 4, L equal to 0, 1, 2, 3, S, P, D, F. So it has F orbitals. So in all these cases, D, C, and B, there is F orbitals. Okay, but for n equal to 3, I think L is equal to 0, 1, 2 up to only. So S, P, D. So there is no F. Okay, so it has only S, P, D subcell. Okay, so the correct answer is A. Okay, because he asks which is not possible. Okay, so in option number A. Okay, students, these are the 6 questions we have discussed so far. So we'll meet again in another videos. Okay, so in the next okay then, bye students.